we talked about ILP with multiple issue processors with static scheduling, and we started with the VLIW approach. So we talked a little bit about deepening pipelines and how there's diminishing returns, so we want to make our pipeline wider. These are called multiple issue processors from the terminology of issuing or dispatching an instruction to a functional unit. So we talked about VLIW epic last time, and we got into the notion of talking about static superscalar, and that's what we're going to focus on today and hopefully lead us into dynamic superscalar. In this context, we're talking about scheduling instructions to functional units of the processor. So the VLIW approach, it was really popular, I want to say in the late 80s, early 90s. There's a lot of excitement around it. People thought it was going to change the world. It ended up not, but it did bring some interesting concepts to computer architecture and also especially to compiler design. So we looked at a 2-wide VLIW machine for a MIPS 32 processor. Hopefully those words kind of made sense to you. If they did, you're learning something. If they didn't, then I guess you got to go back and study a little bit. You got to have knowledge before you can acquire new knowledge. It's a truism. Do you know that the more knowledge you have, the easier it is for you to acquire new knowledge? It doesn't matter what your knowledge is. So the more you become an expert at something, the easier it is to learn how to do other things. Just a little cognitive psychology tidbit for you today. So we talked about bundles of instructions or issue packets. The ABI, remember that term, application binary interface. The ABI is agreed upon between the ISA, the architecture, and the compiler to say, okay, I am an architecture that has double-wide instruction packets, and you need to align the instructions to a multiple of the double word size. If you have variable length bundles, then the hardware has a more complicated job because it has to fetch a glob of instructions and then decode them. That's not the technical term. And figure out where the instruction boundaries are in order to figure out how to decode the instructions. The philosophy of VLIW is to simplify the hardware. What was happening in the late 80s is that hardware designers were finding that it was becoming increasingly harder to design complex computer processors that just kept getting more and more complex. And so they were struggling with that problem. And one of the ideas was to shift complexity to software. So here is a stylized double-wide machine. I need to have like a image of like a double-wide trailer for this part of this talk. Anyway, if we rely on the compiler to schedule instructions to avoid hazards, then we can reduce the amount of hazard logic we need. We also talked about data flow graphs. So here's a data flow graph for this simple loop. Here was a schedule of one way that the compiler could schedule the instructions, and in order to rearrange and overlap these instructions, the compiler has to rename some of the registers. So I'm not going to go into detail about this again, but we talked briefly about load speculation and about predication, which is different from prediction, predication. So we talked about load speculation, the idea that the compiler could lift loads before stores, even when the compiler isn't sure that the load doesn't load from where the store stores. Which would be a raw dependency through memory. If you violate the order of the read after write, then you've introduced a raw hazard through memory. We need a way to determine what the load and store addresses are and then to disambiguate them. The memory address written as a memory operand is ambiguous until you calculate the effective address. Once you know the effective addresses, then you know they point to the same location within the same virtual address space. Not really that important right now. We've talked about branch prediction in the past. Branch prediction becomes more and more and more important as your issue width grows because you have more instructions in your pipeline, and so you want to minimize your squashes and stalls of those, because you're effectively multiplying the cost of stalling and squashing by the width of your pipeline. If we don't extend our issue packet size, if instead we allow different multiple instruction encodings, we need some way for the hardware to know what encoding is in use. And I showed some relatively simple logic, that's on the next slide, that can be used to steer the instruction. And you can do that based on the template, but you could also do that based on reading opcodes of the instructions. This is the beginning of issue logic and the beginning of where we're going to start to transition into what is more traditionally thought of as superscalar processing. And this is where we got to last time. If we have an issue stage and we have hazard detection logic, then what we have is no longer considered VLIW. It's considered static superscalar. Okay, so here we are with our new material. We're only 40 minutes into class today, not too bad. So the big concept in the static superscalar and understanding it is the scoreboard. Scoreboard is a way of tracking dependencies among instructions within all of the pipelines simultaneously. It's a centralized approach. The name derives from the idea of a scoreboard at a sports game, and really at a complicated one such as golf, perhaps, where you've got lots of different players all going in parallel, but they can all see where everyone is in terms of their progress through the course. And if my golf metaphor is completely falling flat for you, I got nothing. Scoreboard is a centralized structure. That's an important concept. And we're going to evolve our understanding of the scoreboard iteratively. So let's start with this idea of a valid bit. So you already know about valid bits in cache. Valid bit means this piece of hardware is storing something that is valid. Great. So what does valid mean here? Well, it's going to mean something related to the state of the register. And when I say register, I'm talking about general purpose registers or floating point registers, since we have a floating point. There's going to be a valid bit appended to every register. The use of the valid bit is written here. So in our issue stage, we're going to read the valid bit while we're reading our operands. Read the register file, and when you get the values of the register file, you also get their valid bit. If the valid bit is clear, so if it's an invalid operand, we're going to stall that instruction that's using that value, and we're going to watch the bypass network to pluck the updated value off of it. So we're basically going to wait at the issue stage, and it could become available from the bypass network from any stage, depending on how the bypass network works. For example, if our ALU operations really only take one cycle, then we can pluck ALU results off of the interstage buffer entering X2 or entering X3 or entering right back. And we can also get the value when it finishes right back as well. We'll wait for all of our operands to be ready. And when they're all ready, then we'll dispatch to the functional units. We're going to do something special in our first stage of each functional unit. We're going to call that a dispatch stage. We're not going to separate out the notion of dispatching, but dispatch and issue are sort of, they're often used synonymously, but here it's actually a little bit important to differentiate the idea of issuing as reading the operands and being able to go versus dispatching, which is actually going. So when we dispatch, we're going to clear the valid bit of our destination register. And what that is going to do is that's going to prevent any instruction that's coming after us from being able to proceed down the pipeline until we produce our result. And we'll set the valid bit of our destination once we get into the write back stage. So this is the very first approach, relatively simple approach. 1 bit needed per register and a pretty straightforward algorithm to deal with it. So a problem with this simple approach is that we would like to be able to have more functional units. We would like to be able to have better prediction. We would like to be able to issue more instructions per cycle, and we would like to be able to allow instructions to proceed down the pipeline at different speeds. And the reason we would like to do these things is because they would make more efficient use of our hardware. We would be able to use more of our hardware more of a time, which would, by intuition, improve our performance. We can add more functional units. It's just add more hardware. It does make our bypass network grow quite a lot, and it does potentially increase the number of resources or the complexity of the resources we use to access our storage elements. So if we added a second memory pipeline, we would need to have the ability to execute 2 memory accesses simultaneously. So adding more functional units is relatively easy. You just are adding more hardware, but you're actually making your hardware less efficient by doing this. Able to now execute more instructions of the same kind, which may help improve some programs' performance. If you have a very heavy integer workload, then having another integer ALU pipeline should allow you to get through that workload faster. If we add new functional units that increase the latency of our pipeline, then that will increase overall how long it takes our instructions to get through. And that is really going to cause us problems for our hazard detection logic and for our bypass network. We're going to have to add many more lines to our bypass network and many more conditions for our hazard detection logic. It also makes that lockstep problem worse, since now, for example, an ALU operation will take 4 cycles to finish instead of 3 cycles. The next big sort of leap we're going to take is to ease back on our lockstep execution. Can we allow each functional unit pipeline to advance at its own pace? If we still lockstep our processor up through dispatching, meaning up through the first stage of all the pipelines, we still fetch instructions in program order, we still decode them in program order, we still issue them in program order, which is important because we can check the dependencies between the instructions that are all in program order easier, and we stall them all together until all their operands are together. And that's still a problem, right? We're still lockstep through that dispatching, which is a problem since you stall one instruction in issue, you're going to stall all of them. But we can allow them to proceed through the pipeline at their own pace, and so we can potentially reduce the amount of hardware we need, especially the number of interstage buffers. So here we're going to be getting rid of, for example, 3 interstage buffers for our X path. The problem that we're going to have to overcome now is that instructions will reach the write back stage in different orders than program order. It introduces a problem that we might have output dependencies. 2 instructions write to the same register, but they go down different pipeline paths, and the instruction that's later in the program writes its result sooner in time. So when you read from that register, you're not going to see the most recent value in program order. That's the problem. We still, like I said, have lockstep through the dispatch. If we don't have lockstep through the dispatch, we end up with an out-of-order execute. It introduces different problems. So right after read, dependencies can become hazards in an out-of-order execute pipeline. Right now, at least, because we dispatch all of our instructions together and we read their operands before dispatching, we can't have right after read hazards. It's impossible for an instruction that is later in program order to write its result before an instruction that's earlier in program order gets a chance to read it. That's impossible to happen because we have lockstep execution until dispatch, and the scoreboard helps with that. If we have branch prediction, if we do what's called control speculation or branch prediction, we may have the problem where a mispredicted instruction can reach the write back stage before the branch is resolved. This can't happen in the pipeline we're looking at here, where we've got the branches are in the X1 because the branches are resolved the same cycle that they're dispatched. But for example, if our branches here were the M pipeline and we had an X pipeline, we might have an instruction that finishes its X pipeline before we figure out the branch outcome. It's just something to think about. And as we make our superscalar pipeline more complicated, we will have to consider this problem. The other big issue that's introduced here is what's called imprecise exceptions. An exception will stop the pipeline and needs to be handled by the operating system. And some exceptions can be fixed by the operating system, and then the program can resume execution. However, in order to be able to resume execution and to fix the problem, the operating system needs to know which instruction caused the problem. When we have out-of-order write-back, we may have an imprecise exception, meaning we may not know precisely which instruction caused the exception. And this may happen because an exception caused by an instruction that is later in the program could have already modified the register file before the earlier one generates the exception. Let's put a concrete example on this. Suppose we have instructions X and Y, and that's the order they are in the program, X followed by Y. And Y finishes and writes to the register file, and then X has an exception. Well, Y modified the state of the processor before X raised the exception, and so the state of the processor is inconsistent with the program order. So the processor state and the exception program counter, so the instruction that caused the exception, are not consistent. And so we need a way to fix that, and we will deal with that as well in the future. For now, I just want you to understand the concept of what a precise exception is or versus an imprecise exception. There's also the notion of processor consistency. This is related to memory consistency, and we're going to revisit these again in the future when we talk about memory consistency and multiprocessors. There's basically two kinds of consistency that we're generally going to talk about, and those are strong and weak. There are shades in between, but let's just stick to these. So strong consistency is also known as sequential consistency, which means that the processor guarantees that program order is preserved within the processor. This is the simplest model to program to and to debug and to handle exceptions with. A weak consistency processor model only guarantees that data dependencies are preserved, which means that the processor can reorder and complete instructions in any order it pleases, but this can make some things much more challenging. Weak consistency can be a higher performance, more performance in the processor because the processor has more freedom to rearrange and do things as it pleases, but more challenging to program. In general, what we find in processors is a strong consistency because of the need for computer programmers to be productive. Memory consistency models, strong consistency ensures that loads and stores happen in program order, and weak consistency allows loads and stores that are independent of each other to be reordered. And generally what we find is that weaker consistency models prevail because of how much influence loads and stores have on program performance. And we already wrapped that up. That should be earlier. And we wrapped that up. So let me end. Yeah. So probably you will not have had enough time to try this stuff out and internalize the knowledge. I know this.